Hi all, welcome to Sidza.com. Now in the second video of this collision theory, we will discuss about the effect of temperature. In the first part, we have learned that a collision can be effective when the reactant molecules satisfy two conditions. Number one is about the threshold energy and the number two is about the proper orientation. So the collision between the reactant molecules is effective only when the reactant molecules have a threshold energy, when they possess the threshold energy, and at the time of collision they should have a proper orientation. After that, the collision will be effective, otherwise it will be ineffective. Means it will not form the product if either of the two conditions is not satisfied. So when a reaction occurs, reactants convert into products when the reactant molecules possess the threshold energy. So this is the reactant, and the reaction can convert into product only when the reactant molecules possess the threshold energy. So when they cross over the energy barrier, they form the product. So that means the rate of a reaction basically depends on the number of molecules possessing this threshold energy. So if you plot here a graph between the fraction of the molecules and the energy, suppose this is the threshold energy. If this is the threshold energy, the area under this graph here, these are the molecules possessing the threshold energy or more than that. So basically these are the molecules that can form product. So this is the area under this graph here, because if this is the threshold energy, the molecules possessing the threshold energy or more than that, only those molecules will be able to cross over the energy barrier. They will be able to form the product. So when they collide, they will form the product. And here, these molecules, this area here, it represents the number of molecules having energy less than this threshold energy. So when they collide, they will not form the product. So from this portion here, from these molecules, their collisions will be ineffective. Means they will not form the product. So that will be the ineffective collision, and you will not get a product. You get a product from these molecules having energy equal to threshold energy or more than that. Right? So here will be the effective collisions. These molecules, they will undergo the effective collisions. So the rate of a reaction actually depends on the number of molecules possessing that particular energy. If we carry out a particular reaction, suppose the reactants convert into the product, and suppose when you carry out the reaction at 25 degrees Celsius, suppose the rate of a reaction here is X. And if I increase the temperature of the same reaction, now if I carry out the same reaction at more than 25 degrees Celsius by about 10 degree. So let's suppose if I carry out the reaction at 35 degrees Celsius, so the increase in the temperature here is 10 degree, right? It is 10 degrees Celsius. What we find, normally we find that the rate of a reaction becomes 2 times. That means it becomes 2x. Means that for every 10 degree rise of temperature, the rate of a reaction becomes double. Okay? For every 10 degree rise of the temperature, the rate of reaction becomes double. Now if you carry out the same reaction again at the 45 degrees Celsius, right? The rate at the 45 degrees Celsius will be now 4x, right? It will be 4x. Okay? So for every 10 degree rise in temperature, the rate of reaction becomes double. Now the question is why? Just increasing the 10 degrees Celsius, the temperature, why the reaction rate becomes double? It's because the area under this graph here, you can see that becomes almost double. Means that the number of molecules possessing the threshold energy, that becomes double. Right? And let's suppose this is the threshold energy here. Okay? This is the threshold energy. And let's suppose the T1 here is the lower temperature, it is about 25 degrees Celsius. So when you look at this graph here at 25 degrees Celsius, the number of the molecules possessing the threshold energy or more than that is this much, right? This is the area. So this is the area. These are the number of molecules possessing the threshold energy, and they will form the product. When you carry out the same reaction at a higher temperature, at temperature T2, let's suppose at 35 degrees Celsius, the graph shifts right towards the higher energies actually. And now see, the threshold energy doesn't change. That still remains the same, but the area here increases. Number of molecules possessing that energy, right? That becomes almost double here. Okay, it becomes almost double here. So you can see here the number of molecules, or you can see the fraction of the molecules possessing that threshold energy becomes double. The number of the molecules having the energy equal to threshold energy becomes double. That's why the rate of reaction becomes double, right? So increasing the temperature, rate of reaction increases. And if you increase 10 degree rise in temperature, almost the rate becomes double, because the number of molecules possessing the threshold energy, that becomes double. Now what about the catalyst? Normally when you add a catalyst, the rate of reaction increases. Suppose you carry out a reaction here, the reactants convert into products, and when you add a catalyst, the reaction rate becomes faster, much faster. Why it becomes faster? It's because the catalyst provides a different path. It provides a different mechanism for the reaction to occur. It can change the route of the reaction. That means it actually changes the threshold energy. It actually decreases the threshold energy for the same reaction, right? So when you carry out, suppose the reaction here, when the reactants convert into products, in absence of the catalyst, suppose this is the threshold energy, and when you add a catalyst in the same reaction, what happens now? Due to the catalyst, the reaction can occur through a different path, means its threshold energy will change. The threshold energy actually decreases. Catalyst actually decreases the threshold energy, right? Now this is the threshold energy in presence of a catalyst. Okay, this is the threshold energy, right? So this is the energy curve here. Okay, and this is the progress of the reaction. So when you look at this graph here, what you see, we find that the threshold energy in absence of a catalyst, without the catalyst, the threshold energy of reaction is very high, and when you add a catalyst, the threshold energy decreases, and when the threshold energy decreases, the rate of reaction becomes faster. Let's again try to understand it like this, from the graph. So when you carry out a reaction, suppose this is the threshold energy, right, of the reaction. In absence of a catalyst, these are the number of molecules which can form the product, because the threshold energy is very high. But once you add a catalyst, the same reaction can occur through a different route. That means the threshold energy of the reaction decreases, right? So catalyst actually decreases the threshold energy. Now let's suppose the threshold energy for the same reaction is this one, right? Since it decreases the threshold energy, now the new threshold energy for the same reaction is this much. That means the number of the molecules which can form the product is now very high. Okay, so when the number of molecules possessing the threshold energy increases, that means the reaction becomes faster, right? So adding a catalyst, reaction rate increases many times because the catalyst decreases the threshold energy of a reaction. So here's the one small question. By adding the catalyst, the rate constant K for the reaction, what will happen to that? Rate constant K, we know that the rate constant K indicates whether the reaction is fast or slow, isn't it? So when you add a catalyst, what happens? Rate constant K will increase. Okay, it will increase. Now next question is the activation energy of an exothermic reaction A into B, right? Suppose we have a reaction, an exothermic reaction, and here A converts into B, The activation energy is 80 kilojoules. The heat of the reaction is 200 kilojoules. Heat of a reaction basically means the difference between the energy of the reactants and the products, right? We have an exothermic reaction. For an exothermic reaction, the reactants have a lower, the reactants have a high energy and the products have less energy, right? So always when reactant has a high energy and the product has lower energy, it will be exothermic, isn't it? You can see here the difference in the energy. Reactants have very high energy, products have less, so this is the process will be the exothermic. If it is endothermic, in case of endothermics, reactant molecule has a less energy and the products have high energy. So for the endothermic processes, for the endothermic reactions, reactants have actually lower energy and the products have high energy. But for the exothermic, in this case we have a exothermic reaction, right? So it says exothermic reaction, which means that reactants have high energy and the products have a lower energy. And in this reaction, what is the enthalpy? What is the heat of a reaction? You can see this is the heat of reaction, okay, which is about 200 kilojoules. See here, it is heat of reaction is 200 kilojoules since it's exothermic. So this is the amount of energy which is released. The activation energy for the same reaction is what? 80 kilojoules, right? So that means the activation energy here is how much? Activation energy EA here for the reaction is 80 kilojoules. What will be the activation energy for the backward reaction? Right? It will be 80 plus 200, right? So it will be activation energy for the backward reaction will be 280, right? Kilojoules per mole for the backward reaction when the products convert into the reactants, right? So this is the option for that. Hope you got the concept. Thanks for watching the video. Bye for now.